Now that we've had quite a bit of practice of first derivative test and second derivative test, finding critical points and inflection points, we're going to be putting all of the information that we can about a graph about a function together in order to produce an accurate, detailed graph. The information that we normally seek are things like the domain, the intercepts, all potential asymptotes, local maximum, local minimum, intervals of increase, decrease, inflection points, and intervals of concavity. So let's take a look at the function that came through an application of crows and whelks. If you remember, crows fly up to drop a whelk onto a rock beach in the hopes to break the shell and have dinner or lunch. So the function that we were working with is this one, and that describes the average number of drops required in order to break the whelk from the height h, where h is bigger than 0.84. We would like to sketch this graph. So we're going to go through all of these steps, collect all the possible information about the graph, and then put it all together. Let's talk about the domain of my function. So domain are all the possible x values that I can plug into the function. In this case, our x is called h. So oftentimes in terms of domain, it's better to think about what is there that I cannot plug in. And it becomes very clear very quickly that I cannot plug in h equals 0.84 because that's what's going to make denominator equal to 0. Every other number I can plug in with no problem. So my domain is everything except for h being 0.84. The next on our list are vertical asymptotes and horizontal asymptotes. Let's start with vertical asymptotes. Remembering when we talked about them a couple of weeks ago, vertical asymptotes are the values near which the function approaches infinity. In terms of functions that are rational, vertical asymptotes will occur when the denominator is 0. So in this case, my vertical asymptote is exactly the value that's not in the domain, h being 0.84. What about horizontal asymptotes? For horizontal asymptotes, you're going to have to do a little bit more work because we're going to have to compute the limit of our function as h goes to infinity. So the limit of 1 plus 20.4 all over h minus 0.84. Okay, remembering how to compute limits, there's a couple of ways to compute this one. But essentially when h is going to infinity, this is a number 20 divided by infinity. So this whole portion is going to go to 0, which means the entire limit goes to 1. So I do have a horizontal asymptote and it occurs at 1. Great. Then I'm going to look for intercepts of x-intercepts and y-intercepts. And I'm going to leave this to you to actually work out, but my intercepts should work out to be x is minus 19.56 and y is minus 23.3. Let's move into the critical points, intervals of increase, decrease, and potential inflection points. So for critical points, remember that the first thing I have to do is find the derivative, set it to be 0 or not exist. In this case, the derivative is provided to me, so I just have to consider two cases. When is the derivative 0 and when does it not exist? With rational functions, this actually becomes a fairly straightforward process. If I give you a fraction, when is the fraction ever 0? The fraction is only 0 when the top is 0. So in this case, this will correspond to top being 0. Now the top here is minus 20.4. That's never 0, which means that this produces no solutions. Okay? Now the derivative does not exist. When does the fraction not exist? A fraction does not exist exactly when the bottom is 0. So I have these two cases that I will always follow, and the bottom in this case is 0 when h is equal to 0.84. So that is going to be one of my critical points, and in fact, this is then my only critical point under consideration. Okay, so I'm going to construct myself, a number line. Just like we have been, I'm going to put all my critical points on it. Now I only have 1.84, and I'm going to analyze the behavior of the function before and after. So I'm interested in the sign of the derivative before and after this point. Okay, so I'm going to pick a number here, let's say 0, and I'm going to plug it into my derivative to figure out if it's positive or negative. You can go through with a calculator, you'll notice that it's negative. I'm going to pick a number after 0.84, plug it into the derivative. You notice that the derivative, in fact, is always going to be negative because no matter what I plug in here, this gets squared and then it turns into negative. Anything squared is positive, so that negative sign in the front guarantees that the derivative will always be negative, which means that my function was decreasing and is decreasing afterwards. So it's not, in fact, a local minimum or local maximum. That's not a big surprise because this 0.84 was a vertical asymptote in the first place. So this is another type of information that is really useful to include on this analysis of the first and second derivative. Now I'm going to do an analogous type of analysis, but on a second derivative in order to discover potential inflection points, and intervals of concavity. Okay, so I'm just going to get a new slide so I don't have to squish everything in here. For the potential inflection points, I'm going to look for when the second derivative is equal to 0 and when the second derivative does not exist. Okay, those are going to be my two main cases here. Now, as before, not only am I given a second derivative, it is once again a really nice one because it's just one fraction. A fraction is only 0 when the top is 0, and a fraction does not exist when the bottom is 0. I would like to warn you here, though, that this type of top-bottom analysis only works if your function is one big fraction. So for example, it wouldn't work on this part here because you don't have one fraction, you have 1 plus something else. So you cannot say that this whole thing is 0 when the top of a fraction is 0. This analysis only works if your function is just one compact fraction all in one, okay? So the top is 0. Well, the top in this case is 40.8. That's never 0, so this produces no solutions. And the bottom is 0, once again, at the value of 0.84. Okay, so in this case, this is my only potential inflection point. And I'm going to draw, once again, a number line and put all of my newly found potential inflection points on it. Having learned from last time that asymptotes are a good thing to note here, I'm going to note that this is actually a vertical asymptote. This immediately tells me that this cannot be an inflection point because there is no physical point there. However, concavity might actually still change around the asymptote. So let's go through the analysis just to see that. So again, I'm going to analyze the behavior of the second, or the sign of the second derivative that will tell me the behavior of the function. I'm going to pick a number here and plug it into the second derivative. If I pick, let's say 0, plug into the second derivative, I notice that it's going to be negative. And then I'm going to pick a number on this side of 0.84 and plug into the second derivative to discover that on this side, the second derivative is in fact positive. So my function was concave down before and becomes concave up after the asymptote. Now, equipped with all of this information about my function, I'm now going to put all of this together on one graph. All right, so I've just copied over all of the information, so I have it right in front of me, and let's start putting everything onto the graph that we've discovered. So first, I know that my vertical asymptote is at 0.84. So let's say this is my 0.84, and I have a vertical asymptote here. Remember that vertical asymptotes actually cannot get crossed. So this already immediately divides my region sort of into two pieces. I also know that this function has a horizontal asymptote at 1. So I'm going to put my horizontal asymptote here at 1. Remember that horizontal asymptotes can get crossed as long as they eventually get approached by the function. Okay, and then in the process of analysis, I've also discovered that I actually do have axes intercept. X and Y intercepts are large negative numbers, so I'm just going to create this kind of squishy axis here and mark this to be -20 here and this to be let's say minus 23.3 there. So my graph goes through the point somewhere near minus 20. So let's say here and at negative 23.3. Now, notice that my function on all of the numbers is always decreasing. So somehow now I have to put function pieces onto this graph, and I know there will be pieces because of the vertical asymptotes. I'm going to have an infinite jump there, but no matter what I draw must be decreasing always. And before my vertical asymptote here, it's decreasing in a concave down manner, and after it's decreasing in the concave up manner. Just this alone creates enough restrictions that there's essentially only one way the function can go. And I strongly encourage you to pause the video right now and try to fit the pieces of the function together yourself before you see me do this. Okay, so pause right now and we'll be back in a second. Okay, so what you really should have is some kind of graph that looks like, that looks like this. Decreasing and concave down, approaching the vertical asymptote, and then on the graph here, decreasing, approaching the vertical asymptote here, and a horizontal asymptote there. Now, we've talked about how to find local maximum and minimum. What about global extrema? The extreme value theorem actually gives us a very easy way to do so. It says that if I start with a continuous function on a closed interval, so a specified interval, then I am guaranteed that my function will attain both global maximum and the global minimum on that interval, potentially at the endpoints. So if we just sketch ourselves an example of a function, doesn't matter what it looks like. Let's say I have a function that looks like this. Okay, what it's saying is if I pick a window that I look at the function through, I'm guaranteed to see the highest point and the lowest point. They might occur at the natural peaks and valleys, at the local maximum and minimum, or they might happen at the endpoints. So for example, if I take a look at this as my closed interval, so if my window is here, then my global maximum, so I'm only considering this piece of the function here, then my global maximum occurs not where it naturally has a peak, but rather at the endpoint here, because it happens to get cut off at the higher point than the natural peak would have produced. The global minimum, though, does occur at a natural spot where the derivative in this case is 0, okay? But what this says is that if you're asked to find a global maximum or global minimum, all you have to check are critical points and endpoints of your interval. You don't have to perform any other kind of analysis. So let's take a look at a problem here. We are given this function that describes the probability of a cell dividing. And we're asked, between times 0 and 10, when is cell likeliest to divide and when is it least likely to divide? So what we're actually asked to find here is global max and global min of this function. Again, that means all we have to check are critical points and endpoints. The endpoints in this case are given to us, 0 and 10. Critical points we still have to find, okay? So in order to find critical points, remember we have to take a derivative, see where it's equal to 0, and see where it does not exist. So the derivative here turns out to be minus 2t cubed minus 8 all over t cubed plus 16 squared. I'm looking for where this is 0. And again, it's one nice compact fraction, which means that it's 0 when the top is 0, which in this case then turns out to be t equals 2. And I'm looking for when the derivative does not exist. Because it's one fraction, this happens when the bottom is 0. And in this case, that is when t is equal to cube root of minus 16. Notice that we can't take cube roots of negative numbers. However, the one thing that disqualifies this root from consideration is the fact that I am only interested on the interval from 0 to 10. And this is most definitely not in the interval. So this not on the interval from 0 to 10, not in the interval from 0 to 10. Okay, so these are my two critical points, but I am only going to take the one that actually belongs to the interval of interest. Excellent. My endpoints are 0 and 10. So all together, I have 3 points that I'm going to plug back into the function and physically discover which one of them yields the highest and the lowest y value. Okay, so all I'm going to do now is actually evaluate my function at 2, at 0, and at 10. That's how powerful the extreme value theorem is. It says if a global max and min occurs, or when it occurs only at critical points or endpoints, which means that I already have all the points I might need. Now I just have to figure out which one is the highest and which one is the lowest. So I'm going to plug all of these back into the function itself, not into the derivative, but into the function. And now all I'm doing is looking at these numbers. Which one's the smallest? 0 is the smallest, which means that this guy is the global min. Which one of these 3 numbers is the largest? 0.083 is the largest, which means that this one is the global max. Okay, so once again, for global extrema, you don't need to analyze the behavior of the function itself. All you need to do is find critical points, endpoints, and plug all of them back into the function itself.